Hello everyone, would like to learn about the differential amplifier. So far we just assumed that signal is single-ended, so the around the bias point VB signal is fluctuating around there. So the problem with this kind of signaling is that if there is any noise nearby, the signal will be contaminated. But for the differential signaling shown on the right hand side, it shares the common mode level and then signal is applied in antiphase. So the single-ended, our signal is represented like V in equal to VB plus small signal variation. But for the differential signaling, we have the VP and Vn, and then it shares the common mode level n plus a differential signal. So half of Vin applied on the positive side and half of the input is applied on the negative side. So the V in from 1 and 2, we assume that we can derive that small signal variation V in would be Vp minus Vn. And the common mode VCM, common mode will be what? Vp plus Vn over 2. So this kind of a signaling give us a differential component and the common mode component. The benefit from the benefit of this kind of a signaling is that if there's any common mode noise, let's say common mode is fluctuating like this, and then the signal move around there. So Vp and Vn. So this is Vp and Vn for the dotted signal. For this kind of case, the input is found by subtraction of those two signal. In that case, VCM variation disappear. So this becomes the immune to, so this kind of signaling is immune to common mode noise. Okay. Example of the noise can be shown in here. Let's say, for example, there's a clock signal running nearby. So clock is a typically square wave like that. If there is any coupling capacitance like this kind of coupling will result in the noise spike on our signal, right? Every time the clock make its transition, the coupling appear on our signal. But if we use like differential signaling, like we have, for example, we have a common source amplifier, and if this coupling is the same, and then through this coupling capacitance, the clock wave, the signal coupling will appear exactly same on our signal. If we subtract those signal, then we will get noise-free signal. Okay. So how to make a differential circuit in brute force way, very simple way, is that just single-ended circuit is here, CS amplifier shown in here. We just place the identical two amplifier like this, and we apply the signal in phase and out of phase. The 180-degree different signal we apply there, and then we take out each output from both amplifier and the even though and then take the difference Vx and Vy as the output. But the problem with this, still there's some glitch in there, but this glitch is in phase with those two the signal on that node. So more in a typical cases, some other techniques to reduce the signal noise coupling is shown in here. In single-ended case, if there is the antiphase, like a inverted phase of the clock, for example, then we place our signal, single-ended signal, in the middle so that the exactly the same coupling capacitance there. But this is not the this is quite difficult to achieve, but this is for illustration purpose. You may think of this kind of idea. So applying if there's any the glitches in antiphase, then coupling through this parasitic capacitance will nullify. So both coupling, so from rising edge coupling will go up, and the falling edge coupling will make it go down. So you will, if you add them up, then there is noise-free the signal. But to make this one work, we have to make sure that CP1 and CP2 must be the same. Another case that, for example, in case of the differential signaling, if the signal, the coupling, noise coupling signal is running in nearby, just right next to our signal, for example, V out plus, near that we have a positive clock running, and for the V out minus, near to that we have a negative clock running. In that case, even though this coupling capacitance is the same for those CP1 and CP2, the coupling shown in V outside will, for example, rising edge, falling edge, noise coupling. The output will have a rising edge coupling, and here out minus side and falling edge coupling. If you take those two subtraction, then we have a still noise seen here. If there is a case something like this, then there's one way to reduce this kind of a coupling by having cross wire connection there. Then the amount of a coupling can be nullified. For example, if the clock rising edge here and falling edge here on the same line, through this capacitance we have a rising edge coupling, and through this capacitance we have a negative edge coupling. So this coupling and that rising and negative coupling, if those are happening at the same time, then we can still we can eliminate those coupling through this cross wire. This is the one technique that, if you don't know, if you cannot guarantee some easy noise cancellation situation, then you may consider that kind of a wire crossing. This is quite handy technique, because if there's any long wire running in parallel, for example VP and VN signal, if you want to make sure some signal noise coupling, say this is running some signal or data, clock or data, there might be coupling there. To reduce the coupling issue, you may make a connection wire crossing wire there through this coupling. So you may have a cross wire in the same distance, then the coupling capacitance will be similarly distributed, and then coupling will be common mode. So if this is running, so Vp side we have a positive coupling, and here Vn side minus Vn side also positive coupling there. If that noise happening at the same time through this wire coupling, so output will be contaminated by the common mode noise like this. So eventually, if we take those two difference, then the coupling, noise coupling will disappear. So this is kind of a circuit called the pseudo differential circuit. The pseudo means we just placing single-ended circuit like this, 2 times single-ended circuit are placed in 2 times. So you use you apply the antiphase input and take out the antiphase output. This is just most simplistic differential circuit, but we call it pseudo because the output side still the coupling or noise appear in common mode. So in this case, noise is appeared in common mode. But this kind of a problem, the problem is that if those two circuits are not exactly matched, I mean, if there's any mismatch on that R or transistor size W over L, if their size it has the mismatch through the process variation, then even though you take out the difference, you may still see the residual noise on the output. So it is important to take out the noise influence on the circuit, even with the common mode. So this kind of a pseudo differential circuit is sensitive to device matching. This is my negative point. This is the pseudo differential circuit in reality. So we apply the signal with the common mode. For the proper common mode, we'll put those input device in saturation region and also maximize the output swing level. So the output common mode is in the middle of the signal range, and with the input signal running with some differential signaling, the output moves nicely within this range. What if there is error or noise onto the common mode level for both input? Let's say if the input is becomes lower than the case, so lower V in Cm, that will create less current on the each transistor, that will bring up the output node voltage. So output common mode will go up. This will go to some non-ideal case where the output common mode is near VDD, so that for the input signal variation, output doesn't have enough signal headroom, so that it will clip like this. So this kind of a distortion happen. So this kind of pseudo differential circuit is very sensitive to input common mode variation, also noise. If there's any noise onto that, that will actually affect the signal performance. So even though you take out, once the signal output is clipped or saturated like this, even though you take the difference, you may see, you does not see the good sinusoid like this. You just will have a clipped output, right? This is not what you want. So this kind of a high sensitivity to the input mode variation become problematic typically. So there should be some way to overcome this issue. The people try to come up with an idea to overcome this kind of a input common mode sensitivity. So our goal is that bring the designer circuit that doesn't impact on the output level, meaning output common mode level, meaning the current must be fixed. So current should not be affected by the input DC level, input common mode level. Only the difference of the input voltage will generate or affect the output signal. That such motivation bring us to the following very fantastic circuit called the differential circuit. This is actual basic differential circuit evaluation. So to limit or make this load current to be constant regardless of the input common mode voltage, we make this kind of current source on the source node. If those M1 and M2 are equal, the same size and same bias voltage applied, so for example VB, if we in CM, so input is at the same bias point, so we in CM plus apply the differential signal over 2. So V in 1 is, let's say this is negative, the V in CM plus V diff over 2. Then V diff is a small variation and V in CM is common mode, input common mode. For this case, if the V diff is 0, then same biasing voltage applied on the gate and same size. So this current on the tail, this is tail current, source will split, the current will split it into 2 branches equally. Why? Because we have the same gate bias voltage for V in 1 and V in 2 and same device size. The current must flow or balance between left and right hand branches. So the same current ISS over 2 will flow through the RD1 and RD2 respectively. So output voltage will be VDD minus times ISS, so output, the common mode level will be at the V out common, CM will be what? VDD minus RD times half ISS. That's where the output bias voltage is sitting on. This is the level here, shown in here. Now, this is at the biasing condition. So everything is balanced, same voltage, equal, left and right hand side, the same voltage on the X and Y, and V in 1 and V in 2, same voltage applied. So this current, in that case, even though input V in common mode variation happen, even though this common mode changes, this current ISS always split into two branches equally. So that doesn't change the output common mode voltage. So this brings us a large tolerance on the input CM variation. So input CM mode variation does not change the branch current, and the output voltage stays the same. Stays same. Okay. Let's take a look at more on the at biasing condition. So at this for equal V in 1 and V in 2 are equal, let's say Q1 point, current will flow equally on the both branches. So the voltage across gate and source will be VTH plus overdrive. Equally, it will set up VTH plus V overdrive. Here, the V overdrive will be determined by what? So, overdrive is square half mu n C. So ISS over 2 will be half mu n COX W over L V overdrive square, right? So we can find that overdrive. Or from the simulation, you can check out the overdrive of both M1 and M2, right? So this is at the biasing condition. Now, if we apply the input signal, bring it up, and lower the V into by the same amount that we increase on the left hand side, let's say delta, V delta and delta. So positive delta and negative delta we apply there. Then we know that the gate voltage, the current will flow more on the left hand side, right? Now you can imagine at certain point all the current ISS will flow through only M1, where so once the V in one at that point, so this is 0, so right hand side no current and left hand side all the current ISS will flow under what condition? So at that condition we can find out the VGS. So VGS will be what? VTH plus how much overdrive voltage will change? VTH plus square root times overdrive. Why? Because this is the square law device. If you wanna double the current, the overdrive must be square root 2 times larger overdrive overdrive voltage should be set up. Then that will lead us to ISS current, right? So the voltage between gate and source will be this much, and also right hand side the voltage difference between gate and source will be what? So that current through the M2 must be zeros, meaning overdrive is zeros. So VTH plus 0 volt will set up. So at that condition, at that point, all the current will flow through the left hand side, and then X will be the lowest voltage. So V in is go up, so that operating point, this is the Vx and Vy, that voltage will set up. So where is that the actual, so if you take out the difference between V in 1 and V in 2, that point, so V in 1 minus V in 2, that gives us what? VTH plus square root times overdrive minus VTH time plus 0. So root 2 V overdrive. So the voltage difference between input two terminals is square root times overdrive voltage. So this the maximum linear range that we can amplify our input signal is up until the difference becomes where square root times overdrive. So this is the output current. This is the output voltage in single-ended. If you calculate the difference, V out 1 and V out 2, you will get this kind of plot, and then that boundary, this critical point, will be minus square root of times V overdrive, and this is the square root times V overdrive. This overdrive voltage is found at that biasing condition, the equilibrium condition. So V overdrive is found when both inputs are same. I mean equilibrium. Meaning V in 1 equal V in 2. Okay. So once that biasing level condition is found, then we can expect that how much input signal range can be applied, and then linear amplification can be done, right? This is just somehow you can double check when you design your circuit how much your input signal range, so that will determine the input signal range you want to amplify. For example, if you want to design a larger overdrive, like even larger overdrive voltage like this kind of characteristic there, so you can increase overdrive. How you can design the overdrive? By changing the size of the M1 and M2, you can control the overdrive voltage, right? For the given device current, if you change the W over L, you will modify the overdrive, right? So in that way, you can design your circuit as you want, okay? Now let's take a look at and the calculated range of the input current mode level to ensure the every device in saturation. So to ensure M1, M2, and M3 in saturation, our in range input current mode range must be considered and designed. So the minimum input current mode voltage will be where? So this, if you bring this current mode down, then Vp will go down. So that will push the VDS of the M3 lower. So there should be a certain voltage limit for M3 in saturation. That will be VDS must be greater than VDS set, meaning that is what overdrive voltage of the M3. And also for that case, the current is flowing both branch M1 and M2 equally, so that will give us voltage plus overdrive 1, right? So overdrive 1 and overdrive 2 is our same. So the minimum input voltage will be what? So starting from V overdrive 3 plus 1 VGS. And the VGS is VTH plus V overdrive 1, right? That would be the minimum input voltage. What about the maximum voltage? In that case, all depends for this kind of an input current mode. In this case, we assume that IM3 is fixed, like I0. So assume that. So this is true when the M3 in the saturation then the M3 is a current source, right? So as long as M3 in current source the fixed current will flow, that means half of the I0 will flow through the RD equally. So output voltage will be what? Just fixed. How much? So V out, Vx and Vy will be what? VDD minus RD times half of the current. So this is the output voltage. So since that voltage doesn't change, output voltage doesn't change for this V input common mode variation, we know that the maximum input voltage will be what? Until when? The voltage difference is until the threshold voltage difference. At that point, this transistor M1 or M2 will be in saturation, right? So that condition, V in CM, is a VTH higher than this Vx or Y, right? So Vx voltage would be VDD minus RD times I0 over 2. Now the plus VTH, that would be the maximum input common mode voltage that we can ensure that everything is in the saturation region. So as you can see, there's the range of the input common mode for this circuit can operate as a differential circuit. Okay. We can also calculate the range of the output common mode level. In this derivation, we assume that the signal gain is large, so the input to this differential circuit is very small. So for the given input common mode level, we know that the M1 and M2 will be stay in saturation when input goes up, and then output voltage goes down, and this on the right hand side, if the goes down, the output node voltage will go up. For this case, when this goes up, so input common mode is CM, how much go down? The drain voltage will go down how much? Around the VTH difference, right, from the gate voltage. That will give us where. So this is the lowest signal swing. On the right hand side, if the voltage goes down, this transistor can turn off and it can go up to VDD, right? Since that the output is connected to load impedance RD. So what about the output common mode level? Output common mode level. So as you can see there, for the output common mode level, starting from output common mode level, the output can go down to go below that. The lowest peak will go below that input common mode level minus VTH. That's gonna be the lowest peak that you can expect from the differential amplifier, right? Once you know that the lowest voltage you can go and the maximum voltage you can go, maximum would be VDD in that case because the RD is loaded, so the I out equals 0, then the output VY will go up to VDD. So the maximum voltage is VDD and the lowest voltage will be, so we'll go there. The VDD is the maximum. Lowest is V input common mode minus, this is the approximation considering the input signal is so small, input signal swing so that the gain is large. So we approximate the input signal range, the max starting from V input common mode minus VTH. That's gonna be output signal range, right? So once we know that, we want to design that, we want to bias the output common mode in the middle of this range. That would be what? VDD plus V in CM minus VTH over 2. So output common mode, we designed that output common mode in that level by adjusting what? I0 to this current, tail current source. You design, so design I0 to place V out common to the this level, right? So this is the way to maximize the output swing in this example, okay? In actual nanometer design, the gain itself is small, so the approximation here, we just assume that the input signal swing is very small and output swing is very large. So when we calculate the output range, we only consider the input CM. But in reality, what we have to consider is that the maximum input swing. So gate voltage, so on the maximum swing, on the left hand side, it can go up to the maximum, and at that point the output drain voltage of the transistor will go to the minimum. So that minimum happen with that the gate level. So when we calculate the output swing range, we start from this maximum V input peak, V max, rather than the V in common. So on the left hand side, some visualized here. So when the maximum swing minus VTH, that would be actually the lowest peak we can have to make sure this trend is in saturation. So in nanometer design, gain is small, so the the output peak swing can be somehow reduced, somehow not larger than before, right? So there is some limited range of the output waveform is supported to ensure that supported in the nanometer design. Okay. So in that case, we have to calculate from the V max minus VTH is the range. So the output range would be what? So maximum would be VDD, and the minimum would be what? V in max minus VTH. That would be the minimum output voltage that we can have. So we at bias, we wanna place the output common mode level in between those range, okay, in the middle of those output range. So this is output range. Okay, let's analyze the small signal gain out of differential pair. So we apply the small signal V less in over 2 positive, a little bit higher, and on the right hand side we apply the negative polarity, the half minus V in over 2. So we raise the input on the left and decrease the input on the right by the same amount. So in that case, we want to have a gain out of each differential side here. Vx minus v out, vy would be v out. So in that case, if you raise the current, raise the voltage on the left, the current through the I and M1 will increase. How much? Let's say that is ID. How about the other side? So if you decrease the gate on the right hand side, the current will decrease through the M2. So that is represented by current, the variation through the drain and gate by the opposite direction from source to drain. Since there is the tail current, the tail current source is shown in here, there's no current variation. So in AC, small signal analysis, there's no current variation, meaning the open circuit in small signal analysis. So what it means that, so increase in current on the in the IM1 side, that such current have to flow, exactly the same current have to flow on the right hand side. So ID on the left, increased ID, that will go to the right hand side. The current direction, this kind of a low to high current direction, represent the current decrease. Left hand side, the current direction from top to bottom is current increase between drain and source, right? So now once we identify the ID, then we can find out the V out would be what? Vx minus Vy. Vx will be what? Minus ID times RD1. If we assume that RD1 and RD2 is same by the RD, then minus RD times RD is the Vx, and Vy would be what? ID times RD. So the final output would be 2 minus 2 ID RD. Now the question is how to find the ID. If there's an ID there, then we know that gate and source voltage variation would be ID over GM. On the right hand side, the same amount, ID over GM. Here is positive, source is positive, and gate is negative now. As you can see there, we draw the KCL around the input network, so here, by the KCL, by KVL, starting from plus V in, so we know that this is 1, the V in over 2, so let's say drop over the gate and source would be ID over GM, and another voltage drop across source and gate would be ID over GM. That would be what? Minus V in over 2 voltage. So finally, ID is what? ID equal to GM times V in. So here 2 ID 2, we'll get the 2x 2 times, right? 2 times, right? Final, we have a two equation, V out minus 2 times ID times RD, and this is first equation, and second equation is ID equal to what? 2 times half GM V in. the second equation. So finally, V out would be what? Minus GM times RD times V in. So AV would be minus GM RD. Surprisingly, this gain equation is just same as the common source amplifier. This is GM of the M1 and GM of the M2. Since we increase the supply voltage on the input and decrease on the input on the right, so same amount of current flow ID and voltage drop here again, ID over GM, and also same amount ID over GM. So this voltage doesn't change. So source node is AC ground, meaning no voltage change. So we can find the equivalent drive. We can drive equivalent small signal model like this, just RD and transistor, and source is grounded, so V in over 2, and the right hand side would be V out over 2, right? So the relationship between input and an output will be what? V out. You can change that V out because V out to V out prime and the input to V input over 2 prime. V in prime. Because if we have the same factor divided by 2, it will be the same by changing V out prime and V in prime. Then the ratio between V out prime and V in prime would be the same, V out over V in. That would be GM minus GM RD. Okay. So this is how we analyze the differential circuit. So what I shown is that the analysis that I showed exactly same as the gain that we derived from the small signal equivalent model, by using the fact that the source node is the AC ground. Okay, this is only true when your input is balanced, like the one input side is positive V in over 2, the other side is minus V in over 2 variation. In that case, the source node is grounded, because what you are doing is the linear analysis. So by the amount, if the amount we change on the voltage will result in the proportional current change linearly, and such linear current increase and decrease such. So far we just assume that the tail current source here, M3, is ideal. So no matter what the voltage across this tail current source within VDS, the current is fixed to the I0. So the equal current is flowing on both branches at the bias condition. So that for any input common mode variation, the branch current is the same with the I0 over 2. Because of the such same current source, current level, the output voltage doesn't change. So for the noise on the in CM, common mode voltage variation doesn't affect change output voltage for CM voltage, right? What if you have the current source with the non-ideal? So for example, RO here, finite output resistance. For input common mode variation, if you have a different the common mode variation, you will see the similar voltage variation of a V in CM in AC, small signal variation. So for here, small variation in V in CM here, you will see the same V in CM variation, right? So Vs is approximated, right? Actual Vs voltage would be what? So 1 GM RO, 1 plus GM RO times V in CM, right? So this GM is, let's say big GM, because that the so each differential pair GM is GM and GM, then overall we have the double the GM here, so G 2 times GM. Okay, so we have a similar voltage variation on the source node that will create what the current through the current variation through RO. That means the voltage variation, how much that will be V in CM, right? Such a voltage variation will cause the current variation, how much V in CM over RO. So such current variation will be splitted into two branches. So V in CM over 2RO will flow equally, and such variation will go through load register. So output CM variation would be so 2RO V in CM. So it is important to have a high output resistance if you don't want the output common mode variation. If you have a large output common mode for like this simple, without output common mode variation, you will get the output swing like this, right? But if you have a large variation on the output common mode, then your swing will be like moving around this common mode variation. Yes, you can, if you look at the difference in the output voltage, you will see same sign, but the penalty is that you are using up valuable output signal range by that the common mode variation. Okay, so without common mode variation, your signal was supposed to even higher swing was supported like that, but with common mode variation, your output signal can be limited by that variation. So it is good to have a high output resistance from the current source on the bottom. To do that, we use the typically large L to increase RO. Okay, so RO is found by the characteristic from VDS and IDS, right? So the slope is 1 over RO. So if you have a large RO, then you will get the less current variation. Okay, here and here, right? So that would be delta I. So we don't want that current variation happen. Okay. So with the finite RO, we have the common mode variation happen. So, but even with the common mode variation, if we take the difference, so Vx and Vy, Vx minus Vy would be what? Would be the sinusoid, like this. Okay. What happen if we have a register mismatch? For example, RD is RD plus R delta. That is RD plus R delta R. So if there's any mismatch between the load register there, then common mode variation will be appear at the load. Why? Because for input common mode variation, current will be split onto the both branches, but this current, so I0 over 2, will see both current, but this current is modulated. So this one is small signal sense. The voltage drop over RO would be V in Cm. Thus that one would be current level V in Cm divided by RO. Half of that will flow on the left. Another half of the current will flow on the right hand side, right? So this current will see that load register like here, that will through that register the voltage will be the current will be converted into the voltage. In that case, the output side, the differential output will have with this component, the signal component, plus Cm variation added onto the output, right? That will create unwanted signal, right? On that, right? So proper operation, it is important to have from the large RO. Second is that the small mismatch. So there are many layout techniques to minimize the register mismatch and device mismatch. So I just only consider that load register mismatch, but there is also mismatch between transistors, right? M1 and an M2 may have different VTH, threshold voltage, or something like that. So for such kind of mismatch, the output should not affected, but with that mismatch, the force input common mode variation will appear on the output difference, right? Appear on the output difference. So small mismatch is important to have the small for small common mode response, input Cm response, on output, differential output, right? Diff output. So we have to have a large RO and small mismatch and good mismatch and good matching between. So good matching. For better matching, good matching, so there are many layout techniques. So, and such topic can be discussed later, but for now, so this is something that you have to consider for differential circuit. Okay.